and welcome to Chapter 3, Section 3. So we finished Chapters 1 and 2. Now we're on to Chapter 3, and we're going to start in Section 3 to hit some very important concepts to get us off on the right foot with a lot of linear equations. So today is all about slope, and you've heard of slope before, but we're going to understand the slope and the rate of change in a couple new contexts. So we've talked about graphing ordered pairs. We know how to do that. But we can now use the rate of change and the slope to solve problems. And we'll see that with some examples coming up. So some vocab, of course, we'll see rate of change and slope. And one key rule to remember for this section is that the rate of change is always change in y over change in x. Another way to think about that is our vertical change vertical over the horizontal. And another way you can write that is with the arrows to signify the direction that we're talking about here. So vertical, what does that mean? Let's draw a little arrow here. Vertical, that means up and down. So how does the graph change up and down? Is a numerator, and then denominator on the bottom, how does it change going left to right? So somehow get this concept in your mind as we jump into some problems here. So here we see a table. We're asked to use a table to find the rate of change. So what you need to have down is this table for this example. So we've got on our x-axis the time that we drive. Our y-axis is the number of miles that we've gone. So we're tracking the distance and the time as they change together. So using this table, we want to find out what is the rate of change. Now, rate of change is a synonym for slope. So anytime you see that, that means the same thing as slope. And we want to explain the meaning. So what does it mean in the context of this problem? So let's look at how those things are changing. Each time x increases by 2, our y's increase by 76 miles. So when we went from 2 to 4, we increased by 2. From 2 to 4, we increased by 2. And from this cell to this one, we increased by 76. And of course, from 4 to 6, we increased by 2 again. And from the second number here to the third number, we get another increase of 76. So our change in y is constant. It's increasing by this amount every time. Our change in x is also constant. It's increasing by 2 every time. So to find the rate of change, we know that we need to do the change in y over the change in x. Now sometimes you'll see these delta triangles here. That just means change. So change in y over change in x. We said y is changing by 76 each time. X is changing by 2. So then with just one more step, we could now simplify this and find out what is the slope, what is the rate of change. So half of 76, what is that? That is 38. And if we remember the units, y is miles. So miles divided by hours. So miles per hour. So what does this mean in the context of this problem? Well, that's how fast the car is going. 38 miles every hour, 38 mph. So we found that rate of change, taking change in distance over the time. We simplify. You could pick 2 points there from our graph, and we already said 76 divided by 2 would give us 38 as the rate of change. And we know that this means the car is traveling at 38 miles per hour. So every hour the car goes 38 miles. So that's what the context means for this real world example. Okay, so here is one for us to figure out. So this table is what you need to have down for this example. Within the table, we see cost as our y variable in dollars. X is the number of minutes used. So we see this is a cell phone plan. So the cost changes with the number of minutes. So the more you talk on the phone, the more it costs. We can use the table to find the rate of change to see how fast the money is being spent based on how many minutes. So we can also explain the meaning of the rate of change. So what is changing? How is y changing every time? Well, from 1 to 2, we get an increase of 1. From 2 to 3, it's still an increase of 1. So our change in y is 1. Now we need to find the change in x. So this is not too bad because these are easy numbers. From 20 to 40, how does it change? Well, it increases by 20. And you see from 40 to 60, it does the same thing again. So what's my change in x? Well, change in x is going to be 20. So we see 1 over 20, which as a decimal, for some reason this problem has a decimal. $1 divided, this is the dollar here, $1 divided into 20 pieces is a nickel. So $0.05 per minute. So that's dollars per 1 minute. So each minute you're on the phone, it costs you a nickel. Which one of these problems says that? So 5 over 1 doesn't look right. 0.5 over 1 is 50 cents. 20 cents is too much. So this looks right to me. The rate of change is a nickel per minute. This means that that's how much it costs you every minute as you're on the phone. So that makes sense. So for this real world example, we figured out the slope. Change in y over change in x gave us A as our solution. Okay, so another real world example. This time we're talking about travel. So what you need to have down is some kind of a picture, some kind of an image of this graph. So the graph on the right here shows the number of US passports used in some specific years. We want to find how did the rate of change, what was the rate of change for this period from 2 to 4? And then also how did it change from the period 4 to 6? So two different slopes that we'll find to solve this problem. So first, we need to think about, in the context of this problem, how will the slope come out? So we already said before, we know it's change in y over change in x. My y is the passports, that's up and down. My x is time, going left and right. So it's going to be how did we change in passports between 2 years divided by how many years went by. So quantity over time. So have this image down as we move forward to the next slide. Okay, so from 2002 to 2004, we'll plot those numbers. We ended with a little under 9 million passports. We started with 7, so we can understand how that changed. And 2 years went by, right? From 2004 to 2002, that's 2 years. So now we simplify, and it becomes very fast. On top, the difference is 1.9 million passports. The bottom, 2 years went by. So as we divide that, we get 0.95 as our rate of change. That's millions of passports per year. So for that period, from 2002 to 2004, this is our rate of change. So in other words, we find that every year we're getting just under 1 million more passports. That's the value of having that number. Just under 1 million is also, you could rewrite it instead of 0.95 million, as 950,000. Either way, it's fine. So likewise, we can do the same thing for the second period. So we can take the numbers given. In 2006, we had a little more than 12 million passports. We'll subtract what we started with, a little under 9. So this is going to represent the change in the number of passports, which this is our change in Y, and our change in X is just the time. So if we simplify that, the difference here, 3.2 million passports, 2 years went by, divide that away, we get 1.6, and that's million passports over 1 year. So every year we get a little over 1.5 million passports between 2004 and 2006. So that's what this means in the context of this problem. That's a rate of change per year that goes by. So what do we know? As we said, over this 2-year period, the number of U.S. passports increased 3.2 million for a rate of change of 1.6 million per year. So that's a lot of passports being issued by the U.S. government. Okay, so for this one, let's take a step back and explain the meaning of the rate of change for those two answers that we just found. So first, what do we know? Well, we know that we're increasing the number of passports given, and that the numbers we found represent the increase per year of passports given out. So let's have this down or something similar to this as we read through this. So for the first 2 years, 2002 to 2004, there was an average annual increase of 0.95 million passports issued. That's the first one. We found that number. Then between the second period, 04 to 06, there was an average yearly increase of 1.6 million passports issued. So the point here is that you recognize that this rate of change number that we find, this 950,000 and this 1.6 million, that this is the number per year. So per year, every year that goes by, this is what we expect as the change in the number of passports the government gives out. So understand that it's an average, and those represents our rate of change. Okay, so 2C. We're looking at this graph. We want to look at how different the rate of changes shown are. So, in other words, let's take the numbers that we already found and compare them. So we found the rate of change between these 2 years. Another word for the rate of change we said is slope, and slope is the incline of the line, right? So this first one is more flat. That was our 0.95. That was our 0.95 million. This one is much more steep, and we said the rate of change here was 1.6 million. So these numbers make perfect sense. The steeper the slope, the higher the incline, the higher the value of the slope should be. So 1.6 is steeper than 0.95. Anyway, we already found these numbers by subtracting the difference in the y's over the difference in the time, and we can compare them. So how are the different rates shown in the graph? Well, we see the greater vertical change between 04 and 06. Another word for this greater vertical change, and please write this down, greater vertical change. Another word for that is more steep. So we see a higher incline. This line is shifted higher up than this line is. It's steeper, it has a higher slope, there is a greater vertical change. So those are 3 ways of saying the same thing. Understand that on a graph, the higher the incline, the greater the slope. It is steeper. Okay, so 2D asks us to look at this graph and understand what's happening. This time we're talking about airlines. So the number of departures, so every time a plane takes off in millions, and we have time going by on the x-axis. So we're asked to find the rate of change for 2 periods of years. First between 95 and 2000, and then from 2000 to 2005. So these 2 periods of time. So we can do that by, first let's do the change in y over the change in x. And this is for 95 to 2000. So what is my change in y? How did the departures change from 2000 to 95? Well, in the year 2000, we had 9 million. And in the year 95, we had 8.1 million. So how did the departures change over that 5-year period? Well, from 9 to 8.1, what's the difference there? It's 0.9 million. So that's our change in the flights leaving. Now, what's our change in time? Well, from 95 to 2000, we know that's 5 years. You could also just subtract 2000 minus 1995, but we already know that's a 5-year difference. So from here, now we could divide this 0.9 by 5, and we would get 180,000. Since this 0.9 is in millions, if we divided it by 5, we would get 0.18 million. And 0.18 million, that's million. 0.18 million, if you rewrite that, that's also equal to 180,000 departures per year. So we already know of these available options, none have 180,000 as an option. So D has to be our correct answer. If we want to go back quickly and double check, from 2000 to 2005, our change in Y is going to be from 9.9 to 9.0 is 0.9. And 5 years went by as well. So we see here we get the same expression. So this is also going to be 180,000. A rate of change is the same. Another way you can tell it doesn't change between all these years, this line is perfectly straight, isn't it? It's not getting steeper, it's not getting flatter, it's staying the same. So the rate of change is constant throughout this whole period. So 180, 180 again. Our answer is definitely D. There are 180,000 more departures every year for all 10 years. Okay, so we can also look at the constant rate of change. And the idea here is to tell if the rate of change is the same, so if x and y are always changing by the same amount, we know that our function is a line, right? Lines have to be straight, so the rate of change, the slope, has to stay the same. So we'll just track the x's, see how they're changing, and hope that they're changing by the same amount. So if we look at our x's here, we can see how are they changing. They're increasing by 1 every time. Now how about our y's? How are they changing each time? Well, we see an increase of 6 again and one more time. So we have to go through and check every point here, but we see the x's are always changing by 1, the y's are always changing by 6. So the question is it linear? Well, we know the slope would be our change in y over the change in x. So since the change in y is 6, x is 1, the slope of our line is 6. So is it linear? Yes. It's a line with a slope of 6. It's a constant slope. So very quickly we found this is a constant rate of change. It does form a line. So this is true because our changes are always the same. Y is always going up by 6. X is always going up by 1. And we see that there. So by the same process here, we can do the same thing. Is this linear? Well, how are my x's changing? Each time. From here, negative 10 to negative 2, I see a positive 8. From negative 2 to positive 6, positive 8. From 6 to 14, positive 8 again. How about the y's? From 5 to 1, we get a decrease of 4. From 1 to negative 4, we see a decrease of 5. And from negative 4 to negative 10, we see a decrease of 6. Okay, these numbers, even though it's a pattern, these are not the same. These are not the same. The change is not constant. For something to be a line, the slope has to be the same all the time. It can't suddenly jump up and get steep or flatten out. And that's what's happening here. It's not staying the same. The steepness is changing. So determining is this linear, we would say definitely not. How do we know that? Our explanation is that the rate of change is not constant. So we found that if you track those, the slope is different. Why? Because the rate of change is not the same. It's not constant. So this has formed something strange that's not a line. So we are good to go on 3b. So with one more we can look at, is this function linear? Well, some of you are probably picking this up by now. If we track the changes here, it's going up by 5 every time. And try to draw this table for this example. If we track the y's, what's happening? Well, 2, 4, 6, 8, we see an increase of 2 every time. If we wanted to write the change in the slope of our thing here, our change in y is an increase of 2. Our change in x is an increase of 5. So what is our slope? Well, it's just 2/5 of the fraction. So it's a line with a slope of 2/5. So pretty flat line, but it's still a line. The changes are constant for y and for x. So what do we know here? The no's are out. Yes, the rate of change is constant. So we should have letter choice A. Good, so we figured this out. We're working through it and understanding these concepts. One more thing to look at quickly, and we'll touch on this as we finish this section next time. But when we're looking at the slope, we can see that it's the change in y in blue here over the horizontal change in red. And when you pick 2 points, you can plug them into what we're going to call the slope formula. And plug those things in, and you will get your value by finding the difference in the points. And we'll touch a lot more on that as we finish this section later, but this is something vital to use today as we move forward.